resilience of networks, and we will learn when a network is losing its giant cluster and cannot function anymore. As we see in the class, we already passed the phase transition to lose the giant cluster. Yeah, but I think a lot of people are watching us on YouTube. So,
yes, so
ready to go.
Network resilience is something we saw in the lectures, and today we are going to see an example of network resilience and what happens when we take out the network part by part on the airline network, which is also something that we saw in the lecture. As you may remember, the airline network is a scale-free network. This is coming to end later. So the first...
I thought this is an important topic for you when you plan your summer vacation. Right?
If you want to go to Honolulu, this is very crucial.
Yeah, if you go to Hawaii,
yes.
This is most crucial.
And if there is like alien attack or something,
yes,
and
also,
the airline around the world.
I hope not an alien attack, but in Israel we don't have many options to travel. We can do it within the country, but it's very hot in the summer, so most people are just leaving by airplane. I mean, you can also do some cruise on Manu, but it's more for old people, right? I mean, what are you doing?
No, not really.
Nobody has the
No,
time.
I took a cruise from Manur.
I took also, okay.
There wasn't that many old people.
Good, so you do okay, party people. So you do it once or twice, and then it's
an airplane.
The whole day it's the same. You just sit there and eat.
Yes.
And you
play cards.
In
the casino.
And when you look out of when you're on board and you look around you, it's just water. So it gets boring. So most people are leaving for vacation by plane, and so Ben Gurion is very important for us and is our hub to the world basically. And now we are going to see how vulnerable the airline network is.
Of course, Ben Gurion is the biggest hub in a small country.
I think we only have 3 airports, right? We have.
We can look.
Yeah, we can look.
Yes.
International airports, we have like 4 of them. One in Haifa, one in Ramon, one in Ben Gurion, and Eilat.
It looks.
Ramon is also international?
Yeah, it's international. It has flights to Dubai, for example.
So yes, we're here, and I think that's.
You have to zoom in. This is very difficult to see.
Yes, but it's a cluster. We have it probably considered very small or private airport.
Well, so many there.
Because worldwide it's many.
There are so many in Israel. I'm surprised. Maybe all the military airports are also included. No, good. Okay, so let's go.
So the first code segment is creating the network, and this is all the attributes of the network of each airport. And
it's the dots on the map.
What?
Like we
yes,
are
the
now
dots,
creating the dots.
We'll see the map later again. The dots, the red dots are airport, and the blue lines between them is flights.
Yeah.
So this line prints the number of airports and the number of flights, and we can see, so all the code in the tutorial I ran previously because it would take up more than half the tutorial, and we can see that we have 7,698 airports and 66,760 flights. So that is the network we are going to be working with.
Well, where did you get the data?
The data, okay, yes. So the data is from Open Flight's database and the internet. It's all available, and we take data sets from that database. That's this part and this part, the flights and the airports.
Yeah.
So now we will.
You also have this app, Flight Radar, you know, right?
Yeah.
Where you can track each flight.
Flights. No, but you took it from a
doesn't
database.
work so well. Sometimes they are on it, sometimes not. Okay, so you get this data. From
Yes.
yeah.
Now we will plot that network on an world map, so it will be more clear, and that code plots that graph, and this is what we get. So we can see, as might
Is
be
this
expected.
sorry to interrupt. So is this a package that you get the world map and all these coordinates? How did you do this? That you have all the GPS coordinates?
Yes, this is that topic.
Can't be future.
Yes.
So this is
That gets you world map.
world map, and then and how do you? From where do you know the GPS?
Because you have, that's one of the attributes of each airport, is the location. So you can use that to plot all the airports on the world map. Is that understood?
Okay.
Yes, so as we might expect, most airports are in Europe and the United States, and large population areas usually have more airports. You can see Russia and Africa pretty less dense. Any question about the graph?
Yeah.
It has some dots in Antarctica, I see.
Yes, those are.
Yeah. Okay.
I'm not sure, but those are probably
No,
islands.
not in the islands, in Antarctica itself.
Yeah, Antarctica, 3 dots.
Yes.
More.
But it doesn't have a connection, or doesn't have roots,
Well,
or it's just too thin to see.
routes are very hard to see. You will see when we look on the example of targeted removal of airports. Even after 1,000 airports, we can barely see the routes, but they are still there. Because if you take the biggest hubs, there will barely be routes.
So probably these are research airports, you know.
Yeah.
Like
Yes,
don't
there
have
are
regular
bases in
flights.
Antarctica, so some of them probably have.
And also there with the islands, when
Yes.
you have this in the
American Samoa.
In the Pacific and
yeah.
Atlantic Ocean. Yes. So now, before we get to the main simulation,
This island there next to Argentina is this Falkland?
Yeah.
Falkland?
Yes.
That's an airport, okay. One airport.
is it still British control?
Yeah.
Yeah, they
Yes.
have a war about
Yes,
this.
of
Yeah,
course.
and it kept,
But in the 90s.
It depends who you ask. If you ask someone from Argentina, he will say that it's still Argentine territory.
yeah.
But the British
This
person
is
will always say that
patriotic.
it's British.
You know, there are Israelis that will tell you that most of Israel is not Israeli territory.
Yeah, but also, it's similar to, no, not quite. I thought it's similar to Cyprus, where you have, depending if you ask the Greek or the Turkish, but actually there's a clear
Yeah, there's a
separation,
clear border.
a clear
But
border.
Falkland
But in
Island is,
Falkland Islands not, yeah.
It has a British military presence, not Argentine.
Right, yeah.
Okay, so before we get to the main simulation of taking out airports, we will write code segments that calculate the 5 biggest hubs. So that will be helpful to see what changes in the network when we take out nodes, and the shortest path between Tel Aviv and Honolulu. So what we get for the complete network uninterrupted is that the 5 biggest hubs So the airports, the 5 airports that has the most flights getting in and out of them are Atlanta, Chicago, Beijing, London, and Paris. So that's.
Surprised Paris. I thought Frankfurt is bigger than Paris.
I was surprised by Atlanta.
No, Atlanta is bigger than New York.
Yes.
Yeah.
Yes, and Chicago is also bigger than New York.
Chicago is yeah.
It's because the distance of the flights. Also, like 30 years ago in Alaska, there was a big airport that had like I think the 3rd place with the most flights.
Oh yes.
Yeah, because 30 years ago planes didn't go that far without refueling. So if you needed to take a flight from Japan to Europe, you would fly to Alaska to. I forgot the name of this airport.
Was it Anchorage?
Anchorage, yeah. To the Anchorage airport, you will fly to the Anchorage airport and then to Europe. And any commercial flights and also like logistic flights will also go to Anchorage. That's why Anchorage is also the biggest city in Alaska, but it's not the capital.
Right.
And that was one of the biggest
Yeah,
airports?
I think it was the 3rd place in the world.
Wow, so that's not true anymore?
But also when you look at the flight routes, they all the time go because the Earth is not really
Yes.
right? It's not really a sphere, so they usually go more in the north. So that's why when you go to Canada, for example, from Europe, you don't go like this.
I was flying from Tokyo to Frankfurt via Alaska and then Canada.
Yes, right. You go. It's shorter to go over the, over the north.
If you wanted, for example, to give each of the airports measurement, to measure the airports, so they would be weighted, you would have to use the cosine rule and stuff like that. But we look at it as not weighted airport. And also the shortest path between Tel Aviv and Honolulu is the least amount of airports between Tel Aviv and Honolulu. So even if, for example, we get that the shortest path is from Tel Aviv to Beijing and from Beijing to Honolulu, that might take more hours than other paths, but they have more connections, so we look at it as longer. Okay? So when the network is complete, this is the shortest path between Tel Aviv and Honolulu.
By flight time, not distance.
Yeah.
Well, not distance and not flight time. Both of them is not what you're looking. The least amount of connections.
So just connections.
Yes, just connections.
It's the possible short.
Yes, that might be much longer in time or in distance than other.
Okay.
So this is pretty close actually, right? If you think about it. So what would be longer when you go?
What would be longer than Beijing?
No, what would be
shorter?
I thought Honolulu is far away, so you have more than two. Here basically you have only one connection.
I don't.
Slide.
Yes.
It's very
with the complete network.
Yeah.
I'm not sure you can find. I mean, you will have to select airports that are very, very like the one in Antarctica and one in the US, but not very popular. So they would have more connections, but Honolulu, the capital of Hawaii and the major airport in Israel. So it would be hard to find a route that is a lot longer with airports that you know off the top of your mind.
Yeah.
But that works.
Even to Tehran, you would be in 2 steps, right? You would fly to Amman and from Amman to Tehran.
You probably could fly from Beijing.
To Tehran, yes, but it could be longer. From
not
time.
But not steps.
But even Pyongyang in North Korea, you would go to Beijing and from Beijing to Pyongyang. So the world is really small.
When we look at it in terms of airline network, because it's scale free and there are very big hubs.
Unfortunately, there are no flights from Beijing to Pyongyang.
There are not anymore?
Never was.
There's no flight from
No. There is no commercial mean to get into North Korea except the train from China. That's the only way you can enter North Korea.
Can you check? Can you discuss?
No, there are probably military airports.
I mean, you have a lot there in Korea.
Yeah, but it's mostly South Korea.
South Korea, yeah. Right.
Yes.
It's just that the doors are too big, but they cover South Korea mostly, not North Korea.
So you don't have no airplanes going into...
You know what? We can look at the
commercial flights.
Graphs
if it's diplomatic flights, yeah, there are flights into North Korea.
We can look at the graph of airport removal when it's targeted, and when we look at that, probably the airports in North Korea will remain.
Yeah,
that makes sense.
That's yes. Okay.
That's
do it later.
Later, okay.
Go
so the main simulation, what we are doing is taking each step 1,000 airports, and then we stop. We calculate. We draw the graph. We look at the graph. We calculate the 5 biggest hubs to see how they change. We calculate also the shortest path between Tel Aviv and Honolulu, if there is such path, and we calculate the number of airports in the largest component. So when we run this simulation, we also protect Tel Aviv and Honolulu, because if we wouldn't, a lot of cases they will be taken out, because we take out airports randomly, they will be taken out and there will be no...
But 1,000 is quite big. I mean, you only have 8,000 airports. If you take out 1,000 at a time, you finish after 6-7 steps.
Yeah, there are 8 graphs. So the tabs
this is just
see overall.
Okay, yes, okay, good.
So first we look at the graphs. We can see that after removing 1,000 nodes, still randomly, yes, most of the airports are still present. It is very random, so there is not something very instant to look. Just at the 1,000 nodes, so less airports, 3,000 nodes, even less airports. The graphs will be more interesting when we look at targeted removal, obviously. So 4,000 nodes, you can see less and less airports, but they are not taken out if there are bigger hubs. So still a lot in Europe and the United States after 6,000 nodes and after 7,000 nodes. So at the end, what the simulation does is take out all the nodes except 50. So there are 50 airports left. This is all the airports except 50, and we can see there are barely connections between them. Probably safe to say there are no connections between them, but no connection randomly we see only after removing a big amount of airports. That will not be the case in targeted removal. So the data we got is after 1,000 airports. There are of course 6,000 somewhat remaining airports. The largest component size is 2,616, and this is the number of components, 4,000. And the 5 biggest hubs are Atlanta, Chicago, Beijing, Paris, and Frankfurt. So Atlanta, Chicago, and Paris were present in the complete network case. So you can see
lot of was removed.
this is randomly. So a small amount of airports changed. Because Beijing wasn't taken out, the shortest path is still the same. When we remove another 1,000 nodes, we can see the largest component size got smaller, also the number of components, and the 5 biggest hubs changed. Two airports that were in the previous step in the 5 biggest hubs were taken out, and the shortest path remains the same. When we look at removing another 1,000 nodes, we can see that changes one airport in the 5 biggest hub changes.
Good, but as long as we have Beijing, there's
Yes.
nothing happening.
Yes, and we
So
can
as
see
we
that
have here
here we
Beijing.
still have Beijing. Here we don't have.
But wait a second, how can now Dallas be?
Beijing has less connections now.
Because you lose connections, okay. Beijing
Yes,
is losing
yes.
connections more than Dallas.
Exactly.
That's why Dallas is now the most connected. Okay. Good.
That is randomly. Here we still have Beijing. Here we don't have Beijing, so we need another airport. We go from Tel Aviv to Frankfurt, Frankfurt to Dallas, and Dallas to Honolulu. And after we remove 7,000 nodes, so there are less than 1,000 nodes remaining, there is no path from Tel Aviv to Honolulu, and only Dallas remains. There are Munich, Las Vegas, Yekaterinburg, yes, and Kiev. And when there are 52 nodes remaining, because 50 in Tel Aviv and Honolulu, we can see that we barely recognize those hubs, and Tel Aviv is here in number 3. So,
What? Tel Aviv
and that
is-
was
yeah,
random.
Because, but Tel Aviv is preserved, so that's
yes, of course. But
Okay.
if it wasn't random, if it was targeted, and we preserved Tel Aviv, it
Yes.
would be number 1 much faster.
Yeah.
So, any questions about this?
So it's pretty resilient to go to Honolulu. So you should.
Yes,
think
and
about
that is because it's a scale-free network.
it.
If it was an exponential network, like the road map of the United States,
Yeah.
it would have been much more destructive. Randomly,
Yeah.
of course. So here we ran the simulation 10 times and average all the results. We'll just check to see that there are that they fit the results we got earlier for one run. We can see the same amount of components in the largest component, and we can see the 5 biggest hubs are well, that is random, but and we average, but they are they make sense. The amount of connections from Tel Aviv to Honolulu is 2.1, so that's interesting. That's probably one run of the simulation that is free. 2.1 again, 2.4, 2.78, so that's mostly free. And then there are there is no connection between Tel Aviv and Honolulu. So yes,
This when
this
it
is
broke down. Yeah.
what?
This when it broke down.
Yes.
Okay.
We can see that after 7,000 removals, it most of the times did not break down. So that's interesting. So it takes really most of the airports to be taken out. So there will be no flights when we take out nodes randomly. Now we will look at the.
But did you have a figure that shows how it's
No.
the case? Oh.
No, it did some problems, figures of the average, but If you don't think it really matters when you have the information.
Okay, so basically it looks like a calculation transition, more or less, right?
Yes.
Oh, okay.
So now we look at the graph we saw in the lecture, graph of the number of nodes in the largest component as a function of how many nodes were removed. And this is in the random case of removing nodes, and also this is average for 10 runs, and this is what we see. This is very interesting because in the lecture we saw that graph, but it was much higher, and at the critical point it went down to 0, while there were a large amount of nodes, and that was the transition. But here, so in that code, we define the critical point, the point from which there is no largest component, the point where there is no connection between Tel Aviv and Honolulu. And because we take out nodes randomly, we can get to a point of that largest component, so to speak, having very little nodes, because there is still a path. So what we see is that as we take out more and more nodes, the number of nodes gets down, and then we get to the critical point and it goes to 0.
Yes. Okay, so yeah, that's not quite equivalent to the calculation transition, but I should have told you. So how would you, I mean, when I showed you 2 weeks ago, I showed you the calculation approach to resilience, right? So how would you make such a figure? I mean, that you see the real transition when the calculation cluster breaks down. Or what would you have to plot against what?
Maximal.
No, what is on the...
It did work for targeted removal.
Yeah, but I
But
think...
if you take not the average size,
Yes,
always
but
the maximal size.
yeah, I mean, usually what do we have on the y-axis for calculation? What do we have on the y-axis?
We have the weight.
The probability to belong to the largest cluster, right?
Mm-hmm.
So, so this is, so basically you have to average over all the probabilities that you have in your network in order to belong to the largest cluster.
Mm-hmm.
So, and this would give you maybe a more abrupt transition. I don't know, one needs to...
In that case, I'm not sure.
But it's not just the average size,
because it will still be continuing like this and not be abrupt, because the critical point is the same critical point. So it
yes,
would resemble the graph from the lecture.
Yeah, but it would go more smooth.
Yes.
Now it goes very steep down, and in this case it would.
Yes, and that's the same for the later graph.
And then it would break down.
Mm-hmm.
So, because if you would plot for the calculation, the size of the largest component, it grows slowly, right?
Mm-hmm.
It grows slowly. But the probability to belong to the largest cluster grows more drastically.
Mm-hmm. Okay.
Okay, good.
Now we're going to look at the example of targeted removal, which means instead of taking a node randomly, so in the previous case we looked at the system, we chose one airport randomly and took it out. Here, targeted removal, the first airport we're taking out is the strongest airport. So it would be, we'll take out Atlanta and so on. And here we of course don't need to run 10 simulation in average, because it also is the same order of removals. So we will look at the same exact simulation like the previous one. So every 1,000 nodes we stop, we plot the graph, and we look 5 biggest hubs, shortest path between Tel Aviv and Honolulu. And so the main thing is, again, we stop every 1,000 nodes. So the results you will get here, first the graphs. So the first graph here of taking the 1,000 nodes, we already see that there are barely flights. So if you look at it very good, you will see some connections. Here there is a connection, and here there are connections, but there are very few.
But why is this?
This is because we took 1,000 strongest hubs.
Okay.
So they broke down the system a lot faster. It would be, if we only looked at targeted removal, we would take very small steps at the beginning. And that is what we did in the next graph. But because we wanted to compare it to the random removal, this is much more strong comparison. The same number of nodes, and we see there are already.
I don't see no flights. Somebody
Yes,
sees
there are. It's very difficult to see.
Okay.
From here, this is a flight. This is a flight.
You don't have nothing between the continents, right?
Yes, very.
It's maybe hidden because the red dots. It's probably domestic flights hidden by the red dots.
Yes. Only domestic flights left.
Yes, so if we continue, so here there is still the flights here, 2,000 nodes, 3,000 nodes. So we take out the same number of nodes as previously, but they are the strongest. So no flights, and 4,000 nodes, 5,000 nodes. Actually, because there are so many airports in Europe and United States, a lot of them are very small and very weak. So that does make sense. 6,000 nodes. I don't think there are any flights at this point. 7,000 nodes, and only 50 nodes. So Tel Aviv and Honolulu are still present.
Because you keep them.
Tel Aviv, yes. And if we look at the data, we will see that after 1,000 nodes, there is already no connection between Tel Aviv and Honolulu.
Yeah, of course.
Yes, and we will later find out that the connection disappears after we take out the 250 strongest airports. We can see that the strongest airport is in Honolulu, which means it's stronger than Tel Aviv, because we protected the Honolulu and Tel Aviv.
If you get as a third place the Inuvik, which is in North Canada, as one of the hubs, then it's already destroyed.
In Greenland, the next one.
Yes.
Greenland, yeah.
So after 1,000 nodes, there is no largest component, and there is also no path. We can see that it just gets smaller and smaller. You see 4 is the largest size, so the system is very, very fractured. And now we will plot the graph for that simulation of the number of components in the largest component as a function of how many nodes we took out. So that is this code. And what we will see is that here this point is 250. That is the critical point. For comparison, the critical point in the previous example is above 7,000 airports. So this graph it's what you said earlier. It's a lot more sleek, but it's also a lot more similar to what we saw in the lecture.
Yeah, that's like the first.
Yes, yes. You can say that this is second and first order, first transition. We can see that below the critical point, it goes down very drastically, the number of components, and then goes to 0.
Yeah.
And if this is all, of course, not an exponential network. If it was an exponential network, there still would be a difference between targeted and random removal, because there is still a difference between how strong the hubs are, but it would be much less different. Very, very close.
Yeah.
That graph and the data.
Yeah.
So that's it.
Okay, very good.
Thank
Thank
you very
you.
much.
Any questions? Now you can play and look.
Look at graphs of.
Yeah, also different connections. How long you take, and then you can.
Yes, not only Tel
compare
Aviv
it.
and
Then you can compare it to what the travel agent is telling you. Maybe it's sending you to
and you
places.
can compare. You can also using digraph compare it to an exponential network. You can build one. There are for sure databases of the United States roads
Yeah. Yeah.
from cities. So
Yeah.
that's also possible.
Right. Okay. Good.
Okay.
So yeah, it will be on GitHub, and then you can check it out.
How much different all this data will be if we like had from the beginning data for airports that especially have only like 50 connections minimum? Do you see something similar, or like a lot of different results?
If you take out this,
if there
you
was
take out
no airports with less than 50 connections from.
Yes, it wouldn't change much. If you do the opposite, it would change very much.
It
Because
would not change much for what? For
he said
the
that
targeted attack.
what would happen if you
I
take
know,
out
yeah,
the
yeah.
weakest airports.
Yes.
So not much. For
No, it would not change.
for
Yeah.
random,
Right.
it would just accelerate the process, because you take out a large number of airports. So randomly, the strongest airports will be taken out faster. But for targeted removal, it would just it would not make it faster. It would make it shorter. Is that understood? Okay.
No, I think for the targeted it would not affect at all, because
Yes, but the whole
Don't
process
even
will be
reach-
shorter because there are less airports. It would not be
yeah,
faster.
but you don't even reach to the 50.
Yeah, we saw the last few airports from Greenland and
You only
Canada.
had,
So it only had like 2 connections.
Right.
Like it's an irrelevant airport for most of the people. You know.
Right.
It's a very small domestic flights probably for the native people, not
Yes,
someone.
yes, yeah.
And also, if you choose, we chose Tel Aviv and Honolulu, which are fairly strong airports. If we chose very weak airports, but also protect them, the same as we did with Tel Aviv and Honolulu, it wouldn't make much difference either, because they are not connected to the weakest airports, even though they are among the weakest airports. So
Yeah.
as long as you look at the connection between two airports, it doesn't.
The whole point of this exercise was to show you how resilient actually the airline network is, because we have the hubs,
Yes.
right? We have hubs, and we still have a lot of hubs. It's not just that we have. If you had a very, you remember we had this generalization of the Farabachi-Albert model, where we had a very capitalistic network where you only have 1 or 2 hubs. So such a network, of course, is very vulnerable to targeted attack, right?
So that's something in the middle.
Yes. So we have still a airline network that is somewhat resilient. Okay, so you need to remove 200 nodes or something. and that you see an effect.
Okay.
Good. Okay. Thank you. Good. So we talked about time series analysis last time. That's where we stopped. Yeah. Okay, so we spoke about, you remember we had this question whether in the residuals, when you remove trends, whether these are polynomial trends or periodic trends, and you have some residuals that look like noise. We asked the question whether there is any information in this noise, and we said yes, you can, sometimes you can apply methods like fluctuation function or detrended fluctuation analysis or the autocorrelation function that Ravid will talk about next week, I think, in order to determine whether there's a memory in the data, right? So this was a way to answer the question whether this noise has any information. Then, of course, we also need to talk about these periodicities in signals, and the most commonly used method to determine this is Fourier transform. We talked about what is the disadvantage of a Fourier transform, which was what? What's the disadvantage of a Fourier transform? Assumes sinusoidal signals, right? And sometimes the signal is something more complex. It's not just a sine, or can be approximated by a sine or cosine, and then you should use wavelets. Today I want to finish the chapter of time series analysis by talking about how to determine phase from a signal and the amplitude of a signal. Talk about Hilbert transform in particular, and then we speak about pairwise coupling, and here in particular about phase synchronization. And perhaps we start now with phase synchronization. Everybody of you knows these movies, right? That if you put metronomes on a wooden board, they synchronize, right? So you have here at the beginning you have 5 metronomes. Each of it has its own frequency, eigenfrequency. They are standing on this board, and not so much happens, right? Why not so much happens there? They are just standing like this on the table. You just continue speaking. Yeah, but when I take this board now and I put it here on these Coca-Cola cans, what happens then? They start to synchronize, right? And why do they start to synchronize?
Because
in this case,
vibrations.
but not in this case. Yeah, vibrations you also have here.
But it's less effective.
Why?
Because the surface is too big.
Because, yes, you need something to transmit the vibrations, right? And in a level that they are not completely damped, you know. And this is.
And it's on a desk, the vibrations are damped by the disk. On the can, they travel to the can.
Hmm?
While it's on the desk, the vibrations just disappear inside the disk.
Yeah, they are too much damped, basically. So, and so I have here the video just to show you again. Sharing. Okay.
This is how procrastination manifests in high performing man. This is me before putting things up.
Good. So what you see here is in the beginning the 5 metronomes, and now he puts them on the pens. And you can see that the board is moving, right? So this is how the metronomes exchange information about their state, right? About their state. And then they start to beat together.
Oh, they're on the cans.
Hmm?
They are on the cans.
Yeah, they're on the cans, otherwise it won't go. Yeah, they put it. But now, one of the most important part of the experiment is that he comes and he takes them down from the cans. Because this way, if somebody shows you this, it's not a proof for synchronization. The proof for synchronization is the adjustment of the rhythm, right? So this is actually now proving synchronization, that when you take this medium out of the equation, that they start to desynchronize, okay? Because they all have a little bit different eigenfrequency, own frequency. So here they start desynchronize. So this is
stop to synchronize.
What?
Why they stop to synchronize?
Why they stop to synchronize? Because now they cannot exchange any more information about their status. They have a little bit different eigenfrequency, a little bit different own frequency. And if they cannot anymore exchange the information about their status, they start to desynchronize. Okay? So that's the important thing, the take-home message, basically. And then, but look at this. Let's see. Copy this. We synchronize an antiphase. How is this happening?
See another oscillation happening. That's how.
What?
There is another oscillation happening in the can movement of the cans.
No, but the cans are not moving much.
But they do move. Small oscillations.
Yeah, so, but intuitively, why should this move in antiphase and before I had this in-phase synchronization?
Because if one moves to this side, so he put the surface to this side from conservation of momentum, and the I don't know.
Yes, but intuitively, why do they get the in-phase synchronization? We just talked about it. The in-phase synchronization happens when they can share information. So how would you get, so basically what do you need to do in order to get them synchronized in antiphase? You need to delay the exchange of information, right? They should be still able to exchange information, but you want to delay this. How do you delay this? By putting a damping, right? You put a damping. The damping is like a chikuch, okay? How do you put here chikuch in this experiment?
I think we changed the metronome itself.
No?
maybe down.
חברה גדולה, אמינה ומפוקחת להלוואות, 7 או 9.
I hate this.
או, ישראכר.
Okay, finally. You can see it here.
I don't see anything different. Ah, the board is smaller.
No.
That's the only difference I see.
No.
The cans are exactly the same.
No, it's not the same. What are these cans?
Ah, they are empty.
They are empty, right?
Okay.
And the other cans, you cannot see them, but they are full, okay?
Ah, okay.
So he didn't put them, but they are full.
That's
When they are
trickery.
full, huh?
They,
When they are full, they don't
they're not facing gas.
Yeah, he
They
should
don't have a liquid in them, that the
he
liquid
should,
also.
he should have done it. Yeah, but it's not turbulent because it's completely filled up. You know, so not much happening there, and it's also very slow movement. So turbulence you can forget.
Does it
But-
matter
but this-
how
this-
much is that field?
It doesn't matter.
Doesn't matter.
No, actually it matters because
Above a certain point
if
or
you
exact number?
yeah, if you would only fill them half, I think it would not work, the experiment. In this setting, okay? Then you have to adjust the frequencies that it
But
works.
you can drink a little bit and it would work.
Yeah, but with cans it's difficult because you have to close them afterwards. But the point is here, you want to delay the exchange of information, right? You introduce a recours, a dumping, and you do this simply here by using full cans instead of empty cans. So that's the trick to get anti-phase
Ronnie?
synchronization. Yes.
If you take a towel and you put it between the surface and the can,
Also works. Good point. Yes, you can also do this with empty cans, but you let them move on a towel. Okay, a towel, or there are some videos where they put some foam or styropor, you know, below, and this also works. Yeah, that's you just need to have the dumping. Yes, and here I put you a nice video, but it's too long. It's half an hour by Stephen Strogatz about synchronization in nature, and it's a really nice TED talk, already 15 years old, but really interesting. If you have some time, I encourage you to check it out. He talks here about synchronization as a really universal phenomenon in nature that actually goes against the third law of thermodynamics. I mean, it's not the entropy, the idea of entropy and the third law of thermodynamics are wrong, but it's a kind of a way to violate in a local setting that entropy is increasing, right? If you have the oscillators, they basically defy the increase of entropy and they synchronize. And this happens in everything oscillating, and since we have many oscillating processes in nature, this is a very frequently observed phenomenon. And Stephen Strogatz speaks about it. So how would we treat this a little bit more formal? When you can just take the easiest set of oscillators, which are Kuramoto oscillators, where you have the derivative of the phase equal to their own frequency, 1 or 2, and then you have a coupling term, right? K sine, this is a sinus coupling term that works on the phases, right? And synchronization you would now simply define as a phase locking condition when the phases of these two oscillators do not, the difference of these phases is bound, right? It's a smaller sum than some arbitrary constant, or you can say instead of phase locking, you can define frequency locking when you just take the first derivatives of the phases. And how would this look like when you plot, for example, the observed phase difference, right? This was the phase difference that we would observe in all the metronomes when we just average their phases, the difference of their individual phases, and you plot this over delta omega. So delta omega is the difference in their natural phases, right? When you start with the metronomes just on the table, and each of it has its own frequency, and you can calculate here the delta omega. So delta omega is calculated when they're on the table, delta big omega is calculated when they are swinging on the board, okay, so to say. And what you see is that for a particular coupling, you get here a range, okay, where they can synchronize, okay. So you can allow yourself, in this case, to go from a delta small omega from minus 0.4 to 0.5 to plus 0.5, and they would still synchronize. If you are out of this range, they would not synchronize, okay? So they need to be sufficiently similar, these omegas. And a famous picture is plotted here, when you just now color basically this phase difference. So here when you have a plateau like this, then the phase difference is 0, right? And you would color this in dark blue, phase difference 0. And when you have a phase difference that is not 0, so depending on its value, you give it a different color. And what you see here is that you have a range of zeros, right? And this grows, so you can allow for a larger frequency mismatch between the oscillators when you have a stronger coupling, right?
Other than dark blue, the colors are random?
No, dark blue is when you have
yes, but the other colors.
No, the other colors increase. So red is the biggest.
More red, it is
yeah, it's more, you have a bigger phase difference. So and this, since it looks like a tongue, right? It's called Arnold's tongue. Arnold was one of the researchers that described this first, and this is usually when you hear people who work
in a bit of a stretch.
Like that, it's like a tongue. I don't know. So it's, but when you hear people who work in chaos theory and nonlinear dynamics, when they talk about Arnold tongue, now you know what it means. It's not the tongue of some colleague, but something that is established. So what happens now when you put here extra noise, an extra noise term? What would you think will happen to this graph? When you put noise, there's no noise on top of this, but we know that you always have noise acting on the oscillators, right? So what would happen with this, in this case?
Nothing.
Why? It's now they have
and we put a
phases
constant, or just we put another constant, or we put another frequency.
Yeah, so you put here a noise term, and depending on the level of the noise, you destroy this plateau, right? So if it's only weak noise, then you have a smaller plateau. But if the noise is sufficiently strong, then you only have synchronization strictly when they have the same frequency, right? Because it's just too noisy to develop synchronization for them.
I don't understand like how the noise relates to the original frequencies. How this new noise relates.
Okay, so it is
like how delta omega, the big delta omega, changes because of the new noise.
Because you have here an omega, an own frequency that is not constant, but it shifts all the time. You know.
Yeah,
so you have a distribution of omega, so to say. So you would have here already an omega plus delta omega for one oscillator. This is the noise term. And then it cannot, if we stay in this picture of exchanging information, it is not a constant flow of information, so to say, but it is very erratic. You know? So the board is moving very erratic, and therefore you cannot get into a state in a
what will happen to Arnold tongue? When you add noise, what happens to Arnold tongue?
Yeah, what happens to Arnold tongue when you add noise?
Get into each other?
It's shrinking. Okay, the blue region is shrinking. Okay, up to a level that it will be. If the noise is too strong, you will just have one straight line. Okay, not so interesting because nothing happens. So the noise is so strong that you oscillators basically don't feel each other, you know. So it's completely meaningless if you have a coupling or you don't have a coupling. Yeah. So the crucial thing for all this endeavor here to calculate synchronization, to see if something is synchronizing, is to calculate the phase, right? So that's the most important thing, to calculate the phase. And there are several approaches to calculate phases on real data, and this depends on what kind of data you have. We will later discuss the most commonly used method, which is applied when you have kind of a cosine or sine signal, sinusoidal signal. This is called the analytic signal approach. Sometimes you have point processes in nature, right? Where you could not apply, you don't have a continuous signal, and you just have flashes of when the cycle is finished, right? So you have only the instance of the beginning of a cycle and the instance of the end of a cycle, and then you would use just a linear interpolation. You would say, okay, beginning of the cycle is 0, end of the cycle is 2 pi, and this is how you calculate your phase. Very simple method called after Poincaré method, and this is used for ECGs, for example, in physiology. Other signals that are not sinusoidal, for example, here's an example of gate force profiles. Okay, that is not a sinus signal, so it's difficult to determine easily a phase here, right? Because how do we get this signal? You see here the first peak. So this is measured when you walk and you have some pressure-sensitive insoles. And when you hit the ground with the heel, you have the first peak, then you roll over your foot, so the pressure goes down, and then you leave the ground and you have another peak, okay? So a analytic signal approach that assumes a sinus signal doesn't work there, and what you would need to do is to use wavelet transform. And we learned last week a little bit about wavelet transform. So what is written here? Somebody remembers what is WT? WT is of course the wavelet transform, but what do you do in order to get a wavelet transform? What is this psi here? Somebody remembers? Was the mother wavelet. Okay, so a wavelet transform is basically that you shift a mother wavelet over the signal. The signal is S of t. The mother wavelet is something that you define. It can be a Mexican head. It can be just a Haar wavelet, which was this Heaviside function. And this you shift over the signal. So you have here a convolution of the signal. And this convolution you can write just as a complex number. Complex number with an amplitude and a phase. And this way you derive the phase. Okay? That is then completely independent of the geometry of the kind of signal that you use. However, the wavelet has to kind of resemble a little bit this signal. So for this kind of profiles, you would choose a wavelet that is similar to how the signal looks like. Okay, so let's focus a little bit on this analytic signal approach, because this is the most commonly used method, and it's very easy. It's you would take the Hilbert transform of your measured signal. So it's formally defined as this integral of the signal you have multiplied by 1 over t. But what it means actually when you solve the math is just shifting the signal, the original signal, by pi over 2. Okay, so nobody actually solves this integral in order to obtain a Hilbert transform, what they are doing is they do a Fourier transform of the signal, right? And then you shift, you have a phase information in the Fourier transform, we talked about it last week, and then you shift your Fourier coefficients by pi over 2, and then you do a reverse Fourier transform. So basically, when you think about it in the 2D space of a complex number, you have your vector for your complex number, and you just add pi over 2. Okay, you add pi over 2 and get your Hilbert transform. For example, if you have a cosine, what is the Hilbert transform of a cosine? Sine. Right? If you shift the cosine by pi over 2, you get the sine wave. Right? Okay, so once you have this, you construct the analytic signal, which is the original signal, plus the Hilbert transform, I times the Hilbert transform. If it's a complex signal, we said we have an amplitude and a phase, and this way you can calculate an instantaneous amplitude just by Pythagoras, right? It's s squared plus the Hilbert transform square, and then the square root. And phi you will get, of course, if it's a vector, you get you take the arcus tangens of the y component, which is the Hilbert transform over the x component, which is s of t. Arcus tangens. This way you get a phase, an instantaneous phase. So the advantage of Hilbert transform is that you have an instantaneous amplitude all the time of the signal, and it can be applied to any signal as long as it has some kind of sinusoidal behavior. And of course it also needs to be narrow banded, because if it is a very broad, frequency, then it is difficult in quotation marks for the Hilbert transform to find the right frequency, because you have a mixture of frequencies. So the Hilbert transform would be difficult for the Hilbert transform to find the appropriate phase of the signal. So let's look at this quick example. As I said, we have a cosine. The Hilbert transform of a cosine is a sine. We build the analytic signal, so it would be cosine plus I sine. Okay, everybody knows what is the amplitude of this, right? It's Euler's formula: cosine square plus sine square, and the square root gives you an amplitude of 1, as you have here, constant 1. And the phase, of course, is just extracted from the exponential function. It's something that just increases over time. Very simple and kind of idiotic example, but I think it's important to understand the methodology and to use it for questions that are more interesting and also a little bit more complicated. For example, we can take now, with this framework that we just learned, we can go now to study the coupling of nonlinear oscillators, like the Rössler oscillator. Rössler oscillator is the formulas for Rössler oscillator are written here, and if you would plot this, you would get an attractor that looks like this, just for the xy coordinates. And this is a nonlinear oscillator, chaotic, and it has a kind of a complicated trajectory. It's not just sine as we saw for the Kuramoto oscillators. And the interesting thing now, when you couple two such oscillators and you apply the analytic signal approach, calculate the amplitude and the phase, the interesting thing you see is that the amplitudes, they are completely uncorrelated. Okay, they are chaotic. So even when you do a strong coupling of these two oscillators, you will never get any correlation between the amplitudes. They change chaotically. So the one is changing completely independent of the other one. However, when you look at the phases, so you take this I e to the power I phi term and you calculate the phase difference, then you see for a strong coupling that they synchronize. So the amplitudes are completely unsynchronized in this case, but the phases are synchronized. Okay? For a strong coupling, this is the coupling constant, you get a phase difference that does not change. If you have a weak coupling, then sometimes you have these phase jumps, right? So you have epochs where they are synchronized and then it jumps to a different level. If you have no coupling, of course, they are not synchronized. So, and a lot of work was done in the past to have this kind of coupled oscillators, not just simple Rösler oscillators, but some more complicated systems, and to see when these systems get synchronized. For example, when I was a student 20 years ago, or more, Michael Rosenkluh and Ido Kanter, they worked on coupled laser systems. So they had chaotic laser systems and they coupled them and they studied when they synchronize, according to what parameters they would synchronize their activity. So this was, and then you could optimize laser design. It was quite interesting work. And so staying with this, the phase synchronization between two coupled Rösler oscillators, so if you would study this over time, right, and you would like to quantify it, a simple way is to look at their phase difference, modulo 2 pi. So this is the phase difference divided by 2 pi, or modulo 2 pi, and in this case it's divided by 2 pi, and you look at a histogram of these phase differences, right? So it can only go from minus pi to plus pi, and then you plot the histogram of this blue example, which would be it would be not coupled, it would be not synchronized, and you would get kind of a flat histogram because you get all phases that are possible. If you have a strong synchronization, like in this case, so it's not very strong coupling, but it's kind of a weak coupling, you get these plateaus, right? But if you plot the histogram of the phase difference, you get some nicely peaked histogram, and this would be an indication of strong synchronization. If you reduce the coupling, then you get fewer and shorter of these plateaus, right? And correspondingly, when you plot the histogram, you will get something that's more broad, right? More broad than this one indicates weak synchronization. But how to put it into numbers? That's the question, right? I mean, you can say strong synchronization, weak synchronization, but usually you want to put numbers on graphs to say, to have a criterion, you know, when to say the synchronization is weak and the synchronization is strong. So how would we do this in this case? Any idea from statistical mechanics that comes to mind? How do you characterize histograms? Have you heard about Shannon entropy? Shannon entropy. Shannon entropy. No?
Yes.
Okay, so Shannon entropy
זה
is
אנטרופיה, מה שאתה מכיר.
the entropy that Shannon defined and
זה
Right?
הרגיל.
So what would you do? You would just define a probability that bin is occupied, pk, right? So actually the entropy is defined as minus the sum over the pk, the probabilities that a bin is occupied, times ln pk, right? Pk, ln pk is Shannon entropy, right? There are different ways to define entropy, but all goes back to Boltzmann, right? It's all kind of a logarithm of occupation of some microstates, right? Right. So this is Shannon entropy. Definition minus the sum over all the pk's ln pk. So if you would have a, let's say, a delta peak, what would you get for a delta peak? If you look at this, so what happens in a delta when you have a delta peak? Then what is your probability, pk? You only have one bin that is occupied, so it's 1, right? And so it's ln 1 is 0, so the entropy S is equal to 0. Okay? So the entropy is equal to 0 when you have a delta peak. Makes sense somehow. What happens when you have a flat distribution? Meaning you have the same probability for each bin. What would you get here? pk is equal to
divided by the number of states.
1 divided by n, right? So you have 1 divided by n. You multiply this by n because you have n terms, right? So you get here 1. And here you get 1 divided by n is 0 minus ln n, right? Minus ln n because it's 1 divided by n. And here you have minus, so the maximum entropy would be ln n, right? It's also a famous question. What is the maximum entropy for the maximum Shannon entropy? The answer is ln n. Somebody asked you. Good. And now you can define basically your index to characterize this histogram. So you can say, okay, let's define it like the maximum entropy, okay, which is ln n, or in this case, minus S that I calculate from the histogram, okay, pk ln pk, divided by S max. And now we said, okay, when we have a delta function, we said S is equal to 0, right? So you would get S max divided by S max is 1. So perfect synchronization delta function would be a rho equal to 1, synchronization index of equal to 1. And if we have here the maximum entropy, would be S max, okay, ln n minus ln n is 0, so it would be rho equals 0 for a flat distribution. Makes sense, right? So we have an index now that can distinguish between strong and weak synchronization. It's a number, rho between 0 and 1. Good. So that's nice. Let's keep it in mind. And let's go to another example. This is real data of postural sway, you know, so you can measure, we did this in the hospital in Chiba, and they have their platforms that measure the pressure, okay, under your feet. And you take participants and tell them, close your eyes and try to stand as still as possible. So they close their eyes, and what happens, and you don't have any control of it, is that you have a swing forward and sideward. You cannot control it. It's your brain is doing it automatically, right? You're not aware of this, but you can measure it, and then you get the red oscillation here, which is for back and forwards, and the black, which is left and side swinging. And you can ask the question now, okay, are these two oscillations synchronized, right? The amplitudes, when you just look at the amplitudes, they are not synchronized, typically, not synchronized. But if you check the phases, so here you have the phase, you calculate by analytic signal approach, you calculate the phase of the left and right swing and the phase of the forward back swing, then you see it is very much synchronized. It's nicely, the phase difference is bound, and you can calculate even synchronization index, and it turns out for healthy people this is nicely synchronized. But if you have somebody with brain damage after stroke or some other neurological disease, it's not synchronized, okay? And they have problems, that's why they also have problems to balance themselves, and they are more prone to fall. So let's just perhaps summarize what you would need to do when you later work in some lab and you want to calculate, you want to determine whether two processes are synchronized. So you would calculate the phase of each oscillator, right, which is done either by analytic signal approach or wavelet approach, or you take, if it's a point process, you just take this Poincaré approach. You calculate the phase difference simply, and here's two examples of real data. One is nicely the phase difference. So the phase difference is constant, and then you have one example where the phase difference oscillates. So if you go to the Arnold tongue, basically one corresponds, the green one would correspond to a value that is nicely within this blue region, the synchronized region, and red would correspond to something that is outside, okay? In this case, it's also, there's also some noise on top of it, so it would maybe look slightly different, the Arnold tongue, but just for the principle, this is how it would look like. And then you identify these the regions of phase locking, or you take the modulo 2 pi in order to plot these histograms. Here you have the histograms. So for the green one, when you calculate the phi, the modulo 2 pi phases, you get a histogram like this, and then you calculate your rho with the approach that I just showed you, Shen entropy S max minus S divided by S max. You get a rho of 0.11, and if you look at the red curve, the phase difference of the red curve, then you would get something that's flat and it's very close to zero. But you see here that in order to get a rho that is significantly high, it needs to be very narrow. Okay, so even this one, you would say, from the picture, you would say, okay, this is highly synchronized, but your rho would be just 0.1.
Is that red or light blue?
No, this is still, this is, okay, maybe it would be more in the light blue than in the dark blue.
If you really go to the extreme red, it would be...
And the extreme red, it's, yeah, so, okay, maybe this would be more, I just put it by, you know, without thinking much, it would be maybe more the orange and red here, you're right. This is really, really flat, yeah. So this would be more over here, perhaps. Yeah. So this way you would calculate whether two processes are synchronized or not. Okay, good. There are a couple of projects on synchronization also. If you want to try it, you can use this approach. And next week or the week after, we have a tutorial on synchronization where you get the code on how to calculate the phase and the phase difference and certain synchronization indices. Good. So we finished for today. Thank you, and see you next week.
Okay.
I don't understand, like, the big psi. Do we see it on the histogram or not?
Yes, the big psi. So this phi is basically a continuous phase. It can run. You know, it can be a 6 pi or something.
Yes.
But this you want to if you want to plot everything in a histogram from minus pi to plus pi, or from 0 to 2 pi, you need to put this modulo. So
no, but on the histogram itself, every point of the histogram is just a value of psi. or what is?
Yes. So each so this would be psi equal to 0, psi equal to 2 pi divided by I don't know how many bins, 100 or something.
Okay.
So this way you fill up all your histogram and count how many times you get.
And we will have a Tirgul how we calculate the rho and S.
Yes, yes.
Because right now I completely don't understand how we do it.
Ah, but it's very, very easy. You
I
just,
don't see how the rho. No, the rho
you
itself.
first
But how do I
make-
find S?
You
itself?
first make this histogram. Histogram
Yes.
is just data. You take all these values and you put it in a histogram, right?
Okay.
And then you calculate the probability. You know how many values you have in the histogram.
Mhm.
So you know you know your n, right?
Yes.
You know your n, and you can calculate your p just by the numbers in this bin divided by the total number. This is 1 over, if it's only one value, if let's say it's 10 values, then it's 10 divided by n. This is your p1, right? Then you do this all for all the p's, and you sum up p, l and p, you sum up and you get your s. It's very simple.
Okay.
Very simple.
Thank you.
Good. Okay.